Hi. Um, so this next method is called the method of the maximum likelihood, and it's for estimating parameters from a known distribution when one or more of the parameters are unknown. So I wrote it down here already. So I have method of maximum likelihood, and we'll define it to say to estimate the parameters theta 1 to theta n. Let's put it in a vector here just to make the notation easier. We pick values that maximize the likelihood function, that maximize Ly given theta hat for sample values y. Okay. All right, so right into an example here. So if, for example, suppose yi is Bernoulli p, and we want to find MLE for p. So just one unknown parameter here. Assume I have a sample of size n, unless I specify otherwise. So we want to maximize the likelihood. So remember, Ly given p is equal to the product of the probability masses. So I have I equal 1 to n. I have p to the yi, 1 minus p to the 1 minus yi. And if you want, you can use indicator function here too. 1, yi has to be either 0 or 1. So you could use something like that. So you want the product of all of that. So taking the product of that, we get this is equal to p to the sum yi. I will drop the n and the 1 there. And I have 1 minus p times to the 1 minus the sum yi. All right. And the last thing just becomes 1. All of those have to be either. So let's just write yi in 0, 1, I equal 1 to n. Okay. All right, so I need to maximize this based on the y's. The y's will give me numbers. When I add them up, I'll get this here. Oh, I didn't do this one right. This should be n. Yeah. Okay. So I will get some number here, p to some power. I will have 1 minus p to some power, and I want to find the p that maximizes this. The idea, of course, is that we don't know p, but that the sample occurred. So the sample, so based on no other information, I might assume the sample is likely to happen rather than unlikely. That seems a better assumption. And I can go from there to get an estimate. So from here to maximize this, sometimes you use calculus, sometimes you use other methods. We'll use calculus, but first we'll take the log. So for simplicity, so for simpler calculation, we take the log, we set L, say yp equal to ln Lyp and maximize Lyp. This will give the same. Same max, because ln is an increasing function. So if I find the max where ln is max, then I have found where ln of L, big L, is max, then that is where big L is max. Okay? All right, so doing this, we can take the log up here. So we have L of y given P is equal to sum yi ln of P plus n minus sum yi ln 1 minus P. And I'll drop the indicator at this point. Otherwise, it's 0. And that's clearly not going to be a max if one of those is 0. So I don't have to worry about that being 0, for example. So continuing, then I get, I want to maximize this, so we take the derivative. So I have d dp L y bar y vector y given P, and taking the derivative here, I get this is equal to sum yi over P plus n minus sum yi over 1 minus P times minus 1. And I set this equal to 0. So doing this, we get what happens. So I can, let's see, add to one side, right? So I get, let's see, so we have sum yi over P, right? Sum yi over n minus sum yi should equal P over 1 minus P, if I did this right. Yep. Or let's take reciprocals. I have, if I take reciprocals, I get 1 minus P all over P, so that's 1 over P minus 1, so I get 1 over P equals 1 plus n minus the sum yi over the sum yi. Now this is just a 1 here and a 1 here, so this is equal to n over the sum yi. So P is equal to 1 over n sum yi, just equal to the sample mean. This is what we found. This is what we've been using for an estimator for P in our problems we've been doing so far. Right. Okay, so in other words, I would take the number of successes and divide by n here. So another way I was, another way we were thinking about this was a binomial random variable, the sum, and then I was dividing it by n. But it really is just the sample mean of the Bernoullis. Okay, what could we, I thought I had a comment about this. Let's see, my notes. Yeah, one thing is, we can see this is an MVUE too, just while we're here. So, so because we showed already the sum yi, or even y bar, is sufficient for P, and y bar is unbiased for P, we know the y bar, the MLE, maximum MLE for P, is an MVUE. Okay, so we have that too. All right, let's do another example. Example 2. Suppose yi exponential with mean equal theta. Okay, so let's find the MLE for theta. So we take L, just one parameter, would be equal to the product, I equal 1 to n, 1 over theta, e to the minus yi over theta. And yeah, if you want, you can have a 1 here, yi greater than 0, something like that, or just greater than 0. Okay, so if I take this product, I get this is equal to 1 over theta to the n, and here I get the sum here. So I have the sum of the yi's times n. I can write that as ny bar, right? So I have e to the minus n y bar over theta here. And yeah, all of these have to be greater than or equal to 0. So I'm just going to say y1 has to be greater than 0. So that will make them all greater than 0. I'm running out of paper here. Okay. So if I continue, I should take the log probably here. So I'm going to stop. I'll continue on the next video. No, I should finish this one. Okay, so taking the log, take the log. Log gives me little l is equal to, so I have the log of 1 over theta to the n, so that's theta to the minus n, so minus n ln theta. And taking the log of the other term gives me minus n y bar over theta, set equal to, take the derivative now, so d theta l, I get minus n over theta. Here I have plus n y bar over theta squared, set equal to 0. The n's cancel. So when I set equal to 0, the n's cancel, and I get y bar over theta squared equals 1 over theta, or again, theta equals y bar. Turns out this is also an MVUE, okay?